Well, I think we're ready to begin here. Carey, for those of you who have signed up since Carey and I have just been here chatting about football and other things, my name is Gary Moore. I'm with UE Systems. We manufacture the ultrasonic equipment from all the Ultra Pro 100s to 1000s up to the new Ultra Pro 15. They get used for a variety of reasons around industrial plants for things. Today what we have is Carey Repasz, who's with Allied Reliability, teaching us a little bit or helping us with which technology we want to apply to which failure mode, what kind of things. You know, you've got a toolbox full of different things, how to use them most effectively. So we're real happy to have you, Carey, and thank you for taking time out to do this. If you have other people that were not able to join us today, I think I'll click on this record button and I will try to keep a recording of this and get it up on our website so you can come back and watch it at a later date. So welcome to back up one, UE Systems. It's what we do. We actually are constantly striving now to bring our customers more and better valuable information so that you can get your reliability program up and running the best that you can. We know that if we can get you operating well, that you're going to become better and better customers of ours, and so that's really our goal. We have offices all over the United States where people can come in and help you if you need some assistance and things like that. Just reach out to us. So I don't want to spend much time about us here. Carey's got a lot of stuff for us. So what I want to do is introduce Carey Repasz with Allied Reliability. And Carey, well, I'm going to actually give this over to you.
Okay, very good.
So I'm going to change the presenter over to you, and as soon as I click this little button, we should be seeing your screen here in just a second.
Okay. And
there you are.
oh, you see me?
Yes,
okay.
I do.
Well, excellent. Let me start the slideshow.
Yep.
Okay. Very quickly, just as a little bit of an intro, the title of our webinar is "Which Technology for What Failure Mode?" And just to kind of set the stage, we're not necessarily going to have a technology discussion. We are going to discuss failure modes, what they are. We're going to discuss some of the foundational elements that are necessary to build a successful condition monitoring strategy. We're going to talk about using RCM principles and apply that to a concept known as failure mode mapping to be able to understand which technologies will even apply to certain equipment types and address failure modes in those equipment types. And we're also going to talk, I'm sorry, back up a little bit. We're going to talk about a concept called equipment criticality. We're going to talk about using that criticality ranking. The understanding of the failure modes in the equipment will allow us to build a strategy. And then very briefly, we're going to talk a little bit about resources and maturity level, talk about where we're going to get started, where we want to be, and what kind of triggers, metrics we can apply to let us know that it's time to be able to expand our strategy to include more equipment. If any of you have heard any other presentations when it comes to the use of what we traditionally call predictive technologies or condition monitoring, the condition monitoring inspections will drive your maintenance costs lower due to the fact that they're more efficient and they're better suited to detect failure modes in our equipment. So basically, this means the more that we can include this into our strategy and the more that we can utilize this, the better off we're going to be and the less money we're going to spend on maintenance. And then the secondary and more telling benefit is that we're going to be able to run our plant better, and the plant makes more money. And this is really important because we want to have an effective strategy. For those of you who were on a couple of minutes early, listening to me and Gary discuss, basically a couple of reasons of why we buy equipment and ends up laying on our shelf, and we definitely want to avoid that. So that's kind of the objectives, and what we're going to talk about is the foundational elements. So we're going to spend a little bit of time talking about equipment hierarchy. We're going to talk about the asset catalog, attribute information that's necessary to build our strategy. We're going to talk briefly about equipment criticality, what it is, why we need to do it. we're going to discuss, some failure nodes analysis techniques, all the way from classical RCM to take us to the failure modes mapping exercise principles, as well as the asset health matrix. And we're going to talk about some of the requirements to be able to build that asset health matrix. The asset health matrix is the basis for what we're going to derive our condition monitoring strategy around. So we're going to take that equipment hierarchy, criticality, our asset health matrix, and we're going to develop what we call equipment maintenance plans. And these equipment maintenance plans include which inspections we're going to do that are going to allow us to detect failure modes early in the life of the failure mode before it becomes a functional failure, so that we can enact further processes such as planning, scheduling, and our work execution to be able to address those failure modes before our equipment's at any real risk for failure. And really, when it comes to leveraging PDM or condition monitoring, that's really the end game, what that's all about. Gary, real quick, I know we're recording, so I apologize. During the presentation, I assume this is just going to be myself speaking, and then we're going to open up questions and answers afterwards?
Yes, Carey. Okay. If I get some people dropping some questions and I can get to you, I'll interrupt you in the interim, but otherwise I'll just let you go and you present it to us, and we'll interrupt you if needed. Okay.
Well, the presentation should take us about 45 minutes or so, depending on how much I jabber. So I'll get through this, and then we should allow ourselves plenty of time to have some discussion afterwards, which is what I really want to get to.
Perfect.
Okay, so first we're going to talk about equipment hierarchy. The purpose of the equipment hierarchy is we're just going to arrange our plant, our processes into a graded structure. In other words, we're going to arrange our equipment and our systems into a structure that we can use to track equipment failures, that we can track cost, downtime, and this also allows us to manage our spare parts, work instructions, and work management. This is going to be very important when it comes to designing our PDM program and putting these strategies into play and managing work. And the hierarchy and our equipment catalog are the most foundational elements. They're also one of the things that are most commonly skipped. Most people, some believe that they have a good hierarchy and a good equipment list, and it turns out that they don't necessarily have a very accurate database. So we end up building our strategy on a flawed foundation, and we don't derive the results that we want. Some folks understand that they don't have strong information about their equipment and they don't have it properly organized, but we still want to jump in to do it to moving into condition monitoring for whatever reason, either pressures from management, our own desires. And what happens is, once again, we don't end up with the result that we intended to have, and we lose steam with our condition monitoring. So this is one that is probably the most important, but unfortunately is also the one that's most neglected. So I cannot stress enough that and the importance of getting our database, getting our equipment list, getting that attribute information arranged properly, and collecting all of that information so that we can build a good strategy. The best part about the hierarchy and the equipment list is this doesn't really take a lot of high-end ability. All this takes is some dedication and some manpower out in the plant to collect this information and to validate that our information is correct. So a functional hierarchy, what we mean by functional is we're going to create a structure that allows for good work identification, PDM management. We're going to be able to accurately account for maintenance costs, and we're not just going to account as a whole, but we're going to be able to understand where we're spending our money as well. The same with failure tracking. We're going to understand which equipment or which systems are causing us the most trouble and allow us to understand where we need to spend our effort. On the same vein, as far as delay or downtime information, this allows us to streamline and manage our spare parts management. And then for planning and scheduling, this allows us to effectively plan the schedule. So these are all of the things that we expect to see. And when we say functional hierarchy, these are the processes that are enabled. So asset validation. Once we've arranged our plant into a logical order, then we're going to collect all of the data and information about our equipment and our systems, This enables all of our subsequent processes that we're going to develop in order to derive our equipment maintenance strategy. So basically, the asset validation is just defining our asset list. Let me move my window down here. There we go. Sorry about that. Their relationships, so how they're related to each other in a systemic sense, as well as the supporting attribute data elements. And when I say supporting attribute data elements, what we mean by that is what type of, the information about the machine that we need to know to be able to determine what failure modes exist, what parts are in that machine. So we're talking things like bearing numbers, gear tooth counts, motor frame size. These are all things for the folks on this presentation who are PDM practitioners immediately go, yes, this is information that I need to know because I need this to build an accurate database. This is also information that we need to know to understand how our equipment fails so that we can properly apply the proper technology to the appropriate failure mode. So this allows, the benefits here are that we're going to verify which assets we actually have in the field. We're going to gather that information to be able to build our subsequent processes. The data scrubbing is that we know we have our accurate data, that our data is accurate. And the important part for the purpose of this presentation is that we're going to have accurate technology database building. And what that means is that we're going to, when we apply the technology, not just apply the appropriate technology to control the right failure mode, but also an understanding of what components and what parts make up those components, that we're able to build the appropriate collection specifications and alarm limits for each applied technology so that we will get the results that we expect. In other words, what we're trying to do is we're trying to apply the technology so that we can identify defects as early as possible. And so we need to have that understanding of what makes up our equipment. This also assists in our criticality process, which we're going to speak about and validate the hierarchy in the plant. So the asset validation, to describe what this is, basically this means an equipment walk down. We're going to go out into the field, we're going to collect all of the relevant information about our equipment, and we're going to update our CMMS or our database to reflect that hierarchy and that data about our equipment. The next step in the process to be able to build a good maintenance strategy is to perform criticality analysis. The criticality analysis is going to help us to define the appropriate equipment maintenance strategy, and it's going to do that by arranging our pieces of equipment and our systems in the plant into a ranking where we have a relative understanding of the importance of each piece of equipment in the plant. Typically how we've built PDM programs in the past, and I'm going to oversimplify, but typically what we've done in the past is we walk through the plant and we go, okay, this one, not this one. We better do this one. We're not sure about that one. We'll wait and see. Or even worse, what happens is a piece of equipment runs a failure, and we react emotionally and say, well, we must need a PM or a PDM on this piece of equipment. And so without an understanding of whether or not it should be included through a strategy, we just throw it on the list. So the criticality analysis helps us take the emotion out of this process and rank these machines so that we understand where we should apply our strategy up front. This is also a foundational element for other processes, for planning and scheduling. We can arrange our backlog and attack the most important pieces of equipment first. If we go into a lubrication excellence strategy, that we understand which pieces of equipment are most important to include in that. And obviously our PM-PDM program design. I apologize for the misprint. RCM, reliability-centered maintenance processes, on our absolute most important systems and pieces of equipment, we're going to go through the RCM process. And also for grading which pieces of equipment or systems we're going to apply root cause analysis. So that CA, for those of you following along, should be RCA, my apologies. So what criticality analysis will do is that we're going to take each function within the plant. We're going to take operations, maintenance, safety. This is going to be tailored to the business needs of each individual type of production environment. We're going to have a series of questions and answers with scores applied to those answers that cover all of those different aspects of what makes our equipment more or less important. So as well as the environmental impact of equipment failures, the safety impact, how much it costs to maintain that equipment, the impact of downtime, the availability of spare parts, and redundancy of equipment. This way, instead of it's only a maintenance-only type of function, every function within our manufacturing environment has had an opportunity to have input as far as what makes a piece of equipment more critical. So instead of an environment where you have competing objectives, all of our business processes are aligned within our plant. So this is why we do this, and these are the different functions that are included. So we determine the ranks of these assets by this quantitative assessment. This tells us where we're going to focus our maintenance reliability efforts, because we understand that through that process we have identified the most important piece of equipment. And since we have all of the different business disciplines within our manufacturing environment participate, this creates that baseline where basically we all agree. We have now what we call a common understanding of what is most important. So one discipline doesn't pull harder than the other because of the facilitation where we've done the criticality analysis. Okay, so now we have an accurate equipment list. We have it arranged in a proper hierarchical arrangement. We have performed a criticality analysis. We understand our most important to our least important pieces of equipment in the plant. Now we can start getting down to quote-unquote the cool stuff. We're going to perform failure modes analysis. And all of the methodologies that we're going to show are trying to accomplish the same thing. We are trying to ensure that we have the appropriate maintenance strategy assigned to each asset. So some of the tools that we have at our disposal, we have the RCM processes. RCM stands for Reliability-Centered Maintenance. Reliability-Centered Maintenance is a facilitated process where we define the system, we define the functions of that system, we define the functional failures of that system, and then we go into the failure modes and effects analysis, and we begin to look at what types of failures can defeat those functions in the equipment. This is very high level. For those of you who have background in RCM, obviously it's very abbreviated and high level discussion. But this facilitated process for RCM typically takes days to weeks per asset or per system to perform. So when we start talking about doing this across an entire equipment database, it doesn't make a lot of sense to do RCM on, say, 1,000 pieces of equipment in a plant. 3 to 5 years later, we'll come back and we're still doing RCM analysis, and we have not enacted any of our strategies, and that just doesn't make any sense. So this is reserved for our most important, most critical systems and pieces of equipment. And typically, most people will tell you somewhere between the top 5 and the top 15% of our systems are candidates for reliability-centered maintenance. So we also have some other things that we can do, the failure modes and effects analysis. And by building a library of that failure modes and effects analysis, we can use what's called failure modes mapping. Failure modes mapping and the asset health matrix is what we're going to focus on. And each one of these methodologies, we're looking at the risk or the consequences of equipment failure. In other words, the unacceptable consequences of those equipment failures versus the resources and cost of each of these methodologies. So understanding these failure modes are what's going to dictate the preventive and the predictive strategies. If we're performing a task that does not have the ability to identify a failure mode, is not regulatory or statutory in requirement, in other words, something that is required by law or statute, or it does not prevent a failure mode, then we are wasting our valuable craft time. And the reason that we bring this up is, as I go to different facilities and different manufacturing plants and have these discussions, the one thing that maintenance managers and maintenance folks in general don't have enough of are two things: money and people. And what we're trying to do through this approach is to optimize that limited resource that we have, and that is our budget and our people that we can use. So this is also one of the most important steps, because quite frequently we're doing tasks and we believe that they're doing the right thing, but we don't necessarily know that we're controlling the failure mode. So this approach allows us to be able to not only validate that we're doing this to the right piece of equipment, controlling the right failure modes, but we also document this so that we can show what our plan is. And this is a very, very important step as well.
Carey, I hate to interrupt you here, but do you have any feel for how much time or effort people do spend where they're applying efforts where they cannot identify a failure or failure mode? Do you have any?
Actually, we do. And Gary, this is focused in PM. And when we get into discussion, I'll pull up a little bit of information if we want to talk further.
Okay.
But typically, off the top of my head, in a PM-based strategy, which is what we find most of our clients and most people in industry to be in, approximately 30% of your PM tasks really aren't doing anything for you at all. Another 30% of those tasks typically can be replaced with your condition monitoring inspections. Another 30% of those tasks are probably targeted to an appropriate failure mode, but are not well written enough. In other words, they're not quantitative in nature, and they're not written with enough detail to ensure consistent execution, that they're not very effective. That leaves us with about 10% of those PM type tasks that are actually effective. Yikes. So when we start talking about integrating our condition monitoring, although it's a little bit out of the scope of this discussion, we definitely have to take a look at what we're doing on the preventive side, because we have to be able to free up those resources, and we also have to, by strategy, be able to apply the appropriate inspection methodology, which is traditionally going to be condition monitoring.
Well,
and
thanks.
That just goes to how equipment fails.
Yeah,
thank you, Carey.
Thanks.
Now, for those of you who have seen, and it's not part of this presentation, but it's another thing that we could bring up after we're done, you know, the studies that were performed by Roman Haas, the studies that were performed by the United States Navy and the aircraft industry basically indicate that about 89% of equipment failures happen in a random, worst new to random pattern, versus about 11% that actually happen in a time-based pattern. So if we go back and just take a really quick high-level view of our own strategy, and we look at the man-hours that we have dedicated to PM versus the man-hours we have dedicated to PDM, and we understand that balance and what it should be, then that allows us very quickly to have a quick understanding of whether or not we're in line with that type of philosophy. So going back a little bit to follow up further on this question, Gary, you know, here's a little bit of what the classical RCM looks like. You know, if we're doing the full-blown classical RCM, we need an outside subject matter expert to facilitate. We're bringing half a dozen people or so into a room. We call the RCM a resource-consuming monster a lot in the industry, because you're talking up to a month per system, and we're also talking about $30,000 to $50,000. So we're talking about something that we don't do very much of because of the cost. We're only going to do this in the most critical systems. As you can see, we have some other methodologies that we can apply that take less time, but still are a significant outlay of resources as well as money. So this leaves us with, we have to have a solution for what I call the balance of plant, or what we call the balance of plant. So what we want to do is apply failure mode mapping. And failure mode mapping is simply, I have an equipment type where I have performed failure modes and effects analysis. In other words, I look at our example of a pump. I know that a pump has a motor, a coupling, a pump. Those are the components in that system. A motor starter, excuse me, don't let me forget the electrical side. And so each of those components are made up of parts. So the motor's made up of the windings, of the rotor, of the bearings. The pump is made up of the impeller, the bearings, the shaft, the housing. Each of those parts have failure modes. That failure modes and effects analysis, once I've used that on a centrifugal pump that is coupled with a flexible coupling, I can apply that failure modes and effects analysis to all of the pumps in my facility. And then also, by knowing which failure modes exist in that pump, I can now, with an understanding of how the technologies work, I can apply and say, for this failure mode, these technologies might apply. And this leaves me with a matrix where basically I have a check mark in a box that says, for a centrifugal pump, and I'm sorry, I've got a misprint on here, and Gary, I apologize. Ultrasound should be checked for every one of those. So boy, there's poor preparation for
that's all right.
For UE systems. But the matrix is very simple. Is I put a check mark basically in the box for each of those technologies that could apply. I can use that. Here's a little bit of a different example. This one actually shows the actual failure mode. So for this part of a bearing, I have a fault of a cracked race due to overloading, then I can use the following technologies for that failure node. A little bit of talk about, I'm going to jump ahead just a couple slides. I'm going to talk a little bit about a failure mode and we'll back up. Typically, the way we address failure modes is a failure mode consists of three parts. We have the part, we have the failure, and the reason. So our example, we have the equipment, and I'm going to take this a little bit up the chain for hierarchy. I have the equipment. Indenture to the equipment are the components. So as we said, the piece of equipment is a centrifugal pump. The components would be the motor, the pump, the coupling, etc. Those components are made up of parts. The way that we kind of differentiate here is the component is usually what we call a line replaceable item, or something that we stock in the warehouse, but is still a repairable item. A motor, for instance, an electric motor is a repairable item. It's made up of parts. Typically, the definition for a part is the lowest unit of common disassembly. So a bearing is usually the lowest common unit of disassembly. We don't repair a bearing typically. We change a bearing. We don't pull a bearing apart and put new rolling elements in it. We just change the bearing, so that makes that the part. When we get to the part, that would be where we have the failure modes. So if we use that example and we put some real-world information into it, we have a boiler feed water pump. A component of that boiler feed water pump is an electric motor. That electric motor has a rolling element bearing, and a failure mode now is that bearing, the part. The failure is fatigued, the failure, and the reason is overloaded. I combine this with the knowledge of how the technologies work, and I can create that failure modes mapping. And so that allows me to create what we call the asset health matrix. And the asset health matrix is where I have that failure modes mapping library in the background, and my equipment arranged in its hierarchy and criticality. And now I understand what technologies could apply. And then the second step is what technologies I will apply. So this is a tool that we're going to use to design and to improve our PM and PDM program. The other thing is since this is a database where I can view this, I have an at-a-glance view of what PDM technologies and PM tasks that I'm going to use to address specific failure modes in my assets in my plant. And these technologies and tasks meaning PMs, are going to be assigned based on the known failure modes of the different components and parts of those pieces of equipment. So what do I need to build an asset health matrix? Well, here's the information I need. I need the plant area. I need the equipment ID, the equipment name, and the equipment description. This is why the foundational element of the hierarchy and the asset validation are so important. I cannot build the asset health matrix unless I have this information and that it's accurate. So then I also want to have a description of the piece of equipment and the equipment type. And this also comes from the asset validation step. The initial output is what we call the 100% theoretical model. The 100% theoretical model describes what the strategy would look like if I were to apply every technology to every known failure mode of my piece of equipment in my plant. This is going to be the basis for program design. Now, common sense tells us that we're not going to apply every technology to every failure mode of every piece of equipment. This is the reason why we perform the criticality analysis, so that we understand where we can best apply our efforts. Because let's be honest, for the people on this webinar who don't have what they would call a good PDM program yet, we're not going to start with the mature model. We're going to start with what we believe we can handle and what we believe our work management processes can absorb and what we can execute. And that's a very important consideration. Getting back into a reason why on the plant floor we get the proclamation of PDM doesn't work, a lot of folks will get into this and say, boy, this is good stuff. I want to do as much as I can. Well, the caution is, let's say that we run out into our plant and we apply every technology that we could. What's going to happen is that we're going to find defects. That's what the technologies are designed to do, and that's what they're going to do when properly applied. When they find those defects, we're going to create a backlog of work. Because they're defects, we need to do something to remove those defects. If I don't have a mature planning and scheduling process, if my craft skills and training and my precision maintenance strategy is not up to snuff, then what's going to happen is those pieces of equipment, even though we know there's defects in them, are still going to run to failure. And here's what we run into is at the plant level, at the floor level, the people operating the machinery, the people maintaining the machinery, the people on the plant floor don't really care that we knew it was going to fail when it breaks. All they care about is that their equipment doesn't run and that we're doing PDM. And so the logical next step is, well, gosh, PDM doesn't work. So we need to understand, and this is where we're going to get into which technology for which failure mode and what we need to do depending on our maturity to create a sound strategy that we can execute. So we start with a 100% theoretical model. Gary, I did a little bit better job of marking where ultrasound applies here.
Thank you.
You're welcome. I'll make sure to update those slides for future use. So this is my database. This is my starting point. So now we start to have a discussion of where we go and where we want to be. This is just a little bit of an example of what are we, why are we doing this? Well, the more pieces of equipment that we have on dedicated under these types of inspections, in other words, the more failure modes we're addressing, the lower our maintenance costs. And you see on the y-axis is RAV, return asset value. That's how we calculate our maintenance costs to a uniform metric is we're going to take the amount of dollars we spend on maintenance versus the value of the facility that we're maintaining. And that's just a generally accepted metric for how we measure maintenance costs. But what we're saying here isn't necessarily that one technology is even better than the other. You'll notice that different ones slope to different areas. This just happens to be the amount that we can apply. You'll notice IR electrical, for instance, ends at 100%. Now, most of our equipment has electric motors, and most of that equipment has electric starters. Therefore, infrared electrical and ultrasound electrical can be applied to 100% of our pieces of equipment. Whereas oil analysis, only a certain number of pieces of equipment have an oil lubricated sum. So it's a lot fewer by percentage pieces of equipment. What we're trying to take from this is basically it's just simple. More is better with the caveat of what we can execute. Real quick before we get in, the last thing that we need to talk about any PDM technology is how it works. And this is one of the most important concepts that we really need to understand and apply, and that is that PDM works through early identification of defects. I'll tell a real quick story about, I got my start as a vibration analyst. And the very first time I made a call with vibration analysis, I had one concern, and my big concern was, will this bearing be bad enough that my peers, the millwrights, the group that I came from, are going to see a bad bearing and believe my technology? Well, that's not really the appropriate philosophy, because basically by the time I had written a work order, any old fool could have told you that the bearing was bad. So basically I'd use a $20,000 instrument to sit and stare at a bearing defect until we really didn't need vibration analysis anymore. As predictive, in the application of the predictive technologies, it is very incumbent upon the people that are administering that and performing that the very moment that we understand what the failure is, so the very moment that we've detected a bad bearing, high resistance in our motor windings, whatever that fault may be, that we report that and get that into the work management system and allow the work management system and the equipment criticality analysis and our processes to take care of when we execute the work. So we need to leverage the ability of each of these PDM technologies. Ultrasound for existence, if I'm using ultrasound to detect bearing defects, if I'm looking for those failure modes in bearings, through that ultrasonic signature, through that function of how ultrasound works, I'm going to be detecting my failures very, very close to the point where the failure starts to occur, or point P on what we call the PDEF interval, which is this graphic. What I need to do is I need to make the recommendation that that bearing has a defect and needs to be replaced. It's not going to get any better. It's not going to heal itself. It's now time for me as a predictive specialist to make the recommendation, make an accurate classification of the fault, enter a work order, and allow the work management system to handle when we execute the work. So we really need to pay attention to that concept, is that the number one thing that our PDM does for us is it gives us time. That's the first thing the PDM gives us, time to be able to deal with these issues. So very important that we, as soon as we recognize what the fault is, we make a recommendation. So now we're going to talk a little bit about actually what the title is. So we're going to talk about selecting the right technology, how we're going to build the strategy. As we said before, the asset health matrix, the 100% theoretical model, shows which technologies could apply. For higher critical equipment, it's going to be appropriate that we're going to apply multiple technologies to detect all of the failure modes in those pieces of equipment. The reason for this is because on the high critical equipment, the consequences of those failures result in an unacceptable condition. What we mean is this could cause an environmental issue. Most commonly, it causes an issue where it leads to excessive downtime, and the monetary impact of that failure on our production rate is unacceptable. So what we need to do is we need, through our inspection strategy, to cover every failure mode, every known failure mode, so that we can identify those early, let our work management processes kick in and allow us to deal with those defects and remove those defects before there's any risk of failure. So all of those failure modes must be addressed on our higher critical equipment. On the less critical equipment, we can use less technologies and more efficient methods, because typically we're looking for dominant failure modes or our most common failure modes on our lesser critical equipment. There's still an impact to that failure. We still want to, there's still value for continued operation, but we can achieve our results with a little bit less of a comprehensive strategy. So this enables detection of the defects that are going to lead to our functional failures and also lead to improvements in our precision practices and qualifications of repairs. So we're going to go into an example. We're just about finished up with the presentation. We're going to look at a story of two pumps here. So our 100% theoretical model for a centrifugal pump, we have a component configuration of a motor starter, an AC induction motor, a grid coupling, and a pump. So as you can see here, what we say is on our failure modes mapping exercise, vibration will apply for the motor coupling of the pump. Ultrasound can apply to all of the components of this pump. Infrared mechanical, infrared electrical to the starter, motor circuit analysis is MCA, and then oil analysis, depending on whether, I guess in this case, our motor is oil lubricated. So this is our 100% theoretical model. This is what we could do. So let's look at one pump. Our first pump has a criticality score of 800 out of a possible 1,000. So very critical piece of equipment. It's a boiler feed water pump. So as you can see, and I'm going to flash back to the theoretical model and move forward to this pump, we basically have taken the 100% theoretical model and applied it to this pump. And the reason is because the consequences of failure are unacceptable. So we are going to throw every technology at every failure mode. The cool part to this strategy, the added benefit is, you'll notice that certain technologies will interlace with each other and complement each other. For instance, if I'm doing vibration on the motor for the purpose of detecting bearing defects, ultrasound is also going to be a useful technology. Infrared mechanical is going to be a useful technology. So now I've got that synergy of those different technologies that increase my certainty of detection. So this is what we're going to do on the most critical piece of equipment. Well, now we've got a pump. It's a hot water makeup pump. This one has a criticality of about 250. This one's got rolling element bearings instead of sleeve bearings, but pretty much the same component configuration. But look at my technology deployment on the low critical piece of equipment. In this case, I'm not going to do vibration analysis at all. I'm going to use ultrasound, understanding which failure modes that I can detect and I can't detect, and I'm going to use infrared mechanical and infrared electrical. I can detect pretty much all of the same equipment failure modes that I can with the other strategy. I might not be able to detect them quite as early in the PDEF interval, but I still have a pretty good plan around the lower criticality piece of equipment. And I'm utilizing my resources in a more efficient manner because now I'm utilizing inspection methodologies that are more efficient to apply and might be something that I feel more comfortable with applying as well. So there's the difference between those two situations and a little bit of a discussion of which technology we might apply based on those criteria. Now we get into a little bit, and I'll very briefly, what we're trying to answer, and we talked about this with the P-to-F interval, is can we identify a defect that can be eliminated? Is it to the right of point P or where there's potential failure on the P-to-F curve? If the answer is yes, we're going to write a work order, and for the purpose of what we call asset health, that asset is now red. Now, if the answer is no, and we've applied all of our inspection methodologies, and there's no defect apparent, then that asset is green. And then I have my last category is if it's an alarm, in other words, I'm going to use standardized alarms on all of my technologies, but there's no apparent defect, and this one is the yellow. And basically this tells me I either have a nuisance alarm or that there is an equipment failure that I have not quite understood what it is yet, and it needs to go one or two directions pretty quickly. And what asset health is going to allow me to do is to understand where I am, from the health of the equipment that I'm monitoring, so I can understand, I can forecast a little bit of how well my plant's going to run. But from a PDM strategy perspective, the asset health is going to tell me when it can be appropriate to expand my strategy as well and bring more technologies online and start to bring my strategy more towards the ideal of what I want it to be when I end up where I end up. So we use benchmark information a little bit to talk about this. So for instance, you know, your best-in-class performers have about 88% of their piece of equipment on vibration, about 70% on mechanical infrared, and then going through, and this is a little bit dated once again, Gary, I'll have to update this with the ultrasonic information. Basically the same with vibration and ultrasonic you're looking at on your mechanical side. So as you can see, in a mature program, you're going to have almost all of your pieces of equipment are going to have some predictive technology applied. This is where we start to talk about what we call asset health management. Asset health management is understanding the asset health and then where I want to be from a strategy standpoint. So I have over here a plant with where I can apply vibration to 3,400 pieces of equipment. Well, these folks have an existing coverage of about 220 pieces of equipment. They have about 135 on oil analysis. They really don't have much of a program yet. But this shows where they need to be when they have a mature strategy, when their resources are built, and when they have the processes that can support this. So for each technology, this shows what that more complete picture looks like. The question is, at what point do I add to my strategy? When can I bring more technologies to bear? When can I address more failure modes? I'm going to use that asset health matrix. So let's say I have a plant, and we'll just say I have 1,000 pieces of equipment in that plant. And I'm going to start with the first, a couple hundred pieces of equipment. And as I put those pieces of equipment on route and I apply that strategy through my asset health matrix, I'm going to begin to measure that asset health. Very simply, the number of pieces of equipment that I'm doing those inspections, what is the percentage of those pieces of equipment that have no defect when the inspection is applied. And I'm going to monitor that, and I'm going to set a goal. In this case, my goal is, let's say, 85% green. So when I get started, I'm going to start with that fourth quartile program, and as I detect those faults, and as I address those faults and remove those defects from the machinery, my asset health is going to increase. As I repair things that I find, as we remove those defects, and as we put the right processes in place to ensure those defects don't come back, I'm going to have growing asset health. Well, at some point, I'm going to reach my target of 85%. And now I'm going to look to see that I can sustain my process. Let's just say, for instance, that I want to see 3 consecutive months where I can hold that 85% of asset health. In other words, I've met my goal. Now I've demonstrated that I can also sustain that. Well, now it's time that I can go to the next step in my strategy. I pull out my asset health matrix and say, let me look at the next group of technologies, or let me look at the next group of equipment that I want to apply technology to. At the same time, in the background, this is where my training is taking place. I'm getting new PDM technicians ready to go. I'm working with a service provider to understand, what I can handle, what I need to outsource, whatever that strategy looks like on the nuts and bolts. This is what I'm doing in the background as we're removing those defects. So now I add more equipment. I'm going to address more failure modes. Well, my asset health is going to go back down because I'm going to find more defects, and basically the process is just going to continue. As we remove those defects, we get back up, we sustain the process, add more pieces of equipment. We're now addressing more failure modes. et cetera, until we get to our end goal where we have a comprehensive PEM strategy. So the summary, we need to start with the foundational elements. In order to build this strategy, I cannot stress enough, we have to start at the beginning. If we jump in the middle, buy some technologies, what's going to end up is we're going to have boxes sitting on shelves collecting dust. And that is not a result that we want to get out of this process. We want a sustainable process where this becomes part of our everyday life, that we're doing these condition monitoring inspections. We need to build this strategy based on failure modes. We need to understand in which ways our equipment fails, apply the appropriate technology and the appropriate PM inspection as well to control those failure modes and identify those failure modes. We're going to utilize our equipment criticality, the relative ranking of how important our equipment is, our process maturity, asset health, where we're going to measure and perform asset health management to determine when we're going to deploy certain technologies and to what equipment we're going to deploy those technologies to. And then we're going to add technologies and machines to our program as dictated through our asset health management principles. If we follow these basic rules, and these are all concepts that really, in essence, anybody, I don't want to oversimplify it, but with a pretty basic understanding of what the technologies are capable of, with a good foundational elements in place, understanding criticality of equipment, we can build this and we can set this strategy and we can put this into play. This accomplishes two objectives. First off, when we request resources, this allows us to make our business case. This allows us to show what our strategy is. And if we want our business case to be accepted, and if we want to our request for resources to be accepted, being able to show that we have done the appropriate steps and have built our strategy based in these steps is going to allow us to get that strategy into play. It's also going to allow us to begin to calculate what type of return on investment we can expect to achieve out of this. So this is what we really need to focus on once we get moving. So that's the end of the presentation as far as that goes. And like I said, not necessarily a discussion of the technologies in and of themselves, but more of a strategic look at how we prepare ourselves to apply technologies, and then how we're going to deploy those technologies through the use of those foundational elements and enabling that strategy.
That's tremendous, Carey. It's amazing as I listen to you go through that, and I'm grabbing the screen back from you as I'm speaking here. But
okay,
it is. I guess it's just very interesting to, look at this process. Do you have? You did touch on this here, but do you have a way a company or a plant can get kind of a fix on where they're at and how much, are they applying the right type of strategy to the right equipment? Is there a way for them to start figuring that out?
Gary, it's pretty much this simple. I mean, basically, that we start from the beginning and we get our asset list in shape. That way we understand, we can benchmark where we are. So let's say that we just want to understand where we are. Okay, right. So what we do is we just take a look at how many pieces of equipment we have in the plant. If we know the equipment type, which most CMMS systems will show you equipment type, then we can build a real quick down and dirty asset health matrix, or we can even take it more simple and say, okay, I have 1,000 rotating assets in my plant, and I'm applying vibration to 200 pieces of equipment. I'm doing ultrasound to 300. I'm doing ultrasound-assisted lube on X number percentage of my motors. I'm doing oil analysis on X number of pieces of equipment. That kind of gives you a little bit of a baseline for where you are. Mm-hmm. You can take this benchmarking information and say, okay, this is what the best-in-class performers do. And then I would recommend Ron Moore's second book, that nice little busy graph I showed up that had the technologies versus cost. Has a really good section discussing kind of exactly that concept. And his second book, I think, is called, it's similar to the title of this. Let me tell you the title of it real quick. I'll jump right to it here. And the title of that book, to give Ron a plug, is called What Tool and When? Selecting the Right Manufacturing Improvement Strategies and Tools.
Yeah.
It's a very similar discussion to what we just had in the past 45 minutes, but it covers a greater depth and a greater span of other process improvement techniques.
Yeah,
So
gotcha.
that's another good reference for folks that kind of want to catch up on that.
So you were saying the first thing you got to make sure you've got an asset list, a list of everything you got, and then you also touched upon criticality. How critical is that piece of equipment to your plant, right? So
Yes.
I mean, I guess it seems like a bit of an obvious question, but is there kind of a formula to figure that out? Is there a way to kind of put a gauge on how critical
Basically,
things are?
and I'll run through this real quick. A lot of folks have equipment criticality. A lot of folks will have something that says 1 through 4, A, B, C, D. Some folks have just a two-part grouping that says critical, not critical.
Yeah.
And that was kind of generally accepted in the past. The problem is when we're looking at building a strategy where we're talking about trying to eat the elephant one bite at a time, so to speak, is that's not enough granularity or not enough detail in that scoring to allow you to implement that strategy over time. So what we recommend is we look at a little bit through statistics, and we also look at it by trying to make sure that we have all of the business disciplines represented. So for instance, we're going to create a matrix, and you can do this any way you want. Some people have fancy tools, but you really don't need it. So for instance, I'm going to have a series of questions that regard production. I might have 4 or 5 questions about production, and that might be, what's the length of downtime for the most common failure of this piece of equipment? What is the cost? What type of customer delivery impact do I have? What type of let me think. What kind of another one might be demurrage and shipping, and it depends on your individual business of what those questions will be. So you arrange yourself about 4 or 5 questions for process, for instance, for the production, what they're concerned with. And then for each of those questions, then they're going to have, for instance, for the length of downtime, is it down for multiple shifts? Is it down for 1 shift? Is it down for a couple hours, or does it really have no impact at all? How much production do I lose? Does it shut the entire plant down? Do I lose a processing line? Do I have to have rework or scrap, or does it really not impact? And you assign a score to each of those. And what you build is, and so you do that for each different discipline. So now the safety and environmental people come in and talk about what's important to them. Is there an environmental release? Is there a potential for chemical release? Is there a fire or explosion hazard? And then you have answers depending on what's important to your individual business based on that. You go through that for maintenance, and you go through that for your spare parts, and you create that. And what you're trying to do is have enough variety of questions and answers. Basically, our rule of thumb is that you want a number of answers that is equal to the square root of the pieces of equipment in the plant. So if I've got 1,000 pieces of equipment in the plant, I want to have the square root of 1,000 for the number of answers I have available. That gives me, in that way, by answering those questions, that's going to allow me to build that score to where I have a good expectation that I'm going to have enough separation between individual pieces of equipment, even ones that are relatively similar, to when I start bringing that strategy online and I want to bring in my next 50 or my next 100, I know exactly which next 50 or which next 100 it is. And the cool part is once you do criticality, then you start to understand all the other uses, your day-to-day uses, such as planning and scheduling. So there's a lot of other, and also is, which parts, which pieces of equipment am I going to stock spare parts for, and which ones am I going to have just-in-time delivery for? So that's a really important part in the process as well, and it's a pretty straightforward thing to do. It just takes time. Right. And that's why those 2 pieces get overlooked so much, Gary, because let's face it, we get excited, we go to a conference, or we get, the local sales rep comes in, shows what these instruments are capable of doing, and people get excited and say, wow, this is pretty cool, I want some of this. The problem is then we bring it in and we don't necessarily know where to apply it, so it just kind of gets thrown up against the wall, and we hope that we get some benefit out of it. and I'm not trying to say this in an accusatory fashion because, hey, I've been guilty of this in the past myself.
Right.
And you have to do those two steps if you're going to have a sustainable process. It just has to be done.
Hey, Carey, this is Doug.
Yes, sir.
We had an emailed-in question here. It's a pretty good one. I think a lot of people probably want to know the answer to this. I mean, how do you actually sell it? Seems like a big initial investment to go out and follow this process that you're talking about. Do you have any experience with, starting small, like an RCM on one process or one piece of equipment, or some type of, I don't know, pilot program or Kaizen events or anything like that?
Yeah, and that's a really good way to get started. There's a couple of ways that you can kind of sell this. Now, obviously, my company, we kind of specialize in helping build business case because the dollars that are at stake and the return on investment is actually pretty huge. So you can look at it from that perspective. And if there's different ways out there to understand, if you measure, for instance, OEE, your overall equipment effectiveness, and you are confident in that number, and you could put a dollar amount and say, okay, now we understand that a metric such as asset health is related to OEE because increased asset health means increased asset availability, and that's 1/3 of our factor there because OEE is basically our uptime of our equipment, the throughput, in other words, how much we're making versus an ideal rate, and then the overall quality of that. Asset health affects two of those three measurements. They affect the throughput, and it affects the uptime of the equipment. So we know that if we can increase that asset health, then that's going to affect that OEE. Now, traditionally, when we get started, we might know OEE, but we don't know asset health. But we can still say, okay, we can go back and we can benchmark some of the companies that have done this for a while and say, we can forecast a 2 to 3% gain in OEE over the next 18 months to 2 years. Here's what that's worth in dollars. That's kind of the big picture business case. Now, moving on to what you talked about as far as a pilot program or, a targeted RCM event. Targeted RCM event is an extremely effective way to go about this because an RCM is a very detailed methodology of what we just talked about. And you're going to develop it, and an RCM is typically performed at a system level. So the first step in an RCM is that you define the system. So you're going to take a bad actor, or basically, to put it more simply, a system, a group of machines that have been kicking your butt, that have a high failure rate, that that you're spending too much resources on, and we do that RCM event. And that RCM event is even more comprehensive than what we talked about. We're going to have an equipment maintenance strategy. We're going to have a spare parts strategy, operator checklist, basically the whole reliability improvement toolbox gets opened up through an RCM event. And it's also great exposure because since it is a facilitated event and you bring in a subject matter expert, then you get that higher level of engagement with that area of the plant. And creating that pilot area is also very powerful because if it's successful and you choose, here's another thing, we want to make sure we choose participants well, that we have a high level of engagement. So now we take this targeted area and we do everything. We just literally throw the book at it. We do everything. We measure our results, and that's going to build upon itself because other people are going to want to do the same thing or say, hey, this is pretty cool. We want some of this. And so the Greenfield project, the targeted area, the pilot plant type of concept is one good method to do this. So that's a really good way to go about that. Did that answer that question?
I think so. Thanks, Carey.
Yeah.
Thanks, Carey.
Okay.
Any other questions, Doug, that you have for him?
No.
What do you are we getting better, or are the plants and companies, are they getting better at employing the right technology, or are we making some headway?
I think so. The hardest part that I see is we still it's very difficult, and this isn't just in the PDM arena. This is basically in life. It's very difficult to basically say, okay, I need to go back to the basics, to the most basic things, and understand what I'm going to try to do. Typically, particularly here in North America, Americans are big on the big thing, fast improvement. Let's throw some technology at it. Let's get going, right? Right. And that creates those challenges and unintended consequences. So that's the biggest challenge. I think we're getting better. Typically, some of the organizations out there that are holding the conferences and kind of pushing the message out, I think are doing a really good job of showing what it takes. I think there's enough good companies out there that people, in my experience, when we take people to benchmark another company, and here's the funny thing that I've noticed over time as well, these top performers, once they're kind of chugging along, they're really willing to let other people, sometimes including their own competitors, come by and have a look at how they do things. Kind of a famous story with one of my clients, they got started by benchmarking somebody who had gone through this journey and done it very well. And they were actually somewhat of a competitor to that other company, and they were pretty amazed. They said, well, gosh, why are you letting us see all this? This is a really serious competitive advantage, and you're sharing it with us. And the other folks that, that were allowing them to benchmark their processes and see how they do things, they actually laughed at them. And they said, well, you're not going to do it because it's hard work. And I think that's what it boils down to, is we got to get, if we get to the basics and we do these things and we do them well, you're going to have success. The argument over whether the technology is effective or not is it's just a dead argument at this point. Mm. For instance, Doug, how long has ultrasound been used in the industry now? Just out of curiosity.
Oh, wow.
30, 20, 30
years, 40 years, probably close to 40 years.
Right. Vibration analysis has been in the industry for about 40 years itself. The time for talking about whether or not the technologies work or not, that time's over. These technologies work, and for the folks that still are going to resist that, they simply need to be educated that they do work. And they've also been demonstrated, they've been applied enough times successfully, and there's companies out there that are enjoying huge competitive advantages due to their maintenance strategy that you just can't overlook whether or not it works anymore. And what people are starting to understand is that we have to do this in an ordered fashion, like any other process, and once we approach it from that type of an angle, yeah, it works great. And yeah. I think that's getting out there more and more.
Yeah, I think
I hope so.
I think you're probably right on the money. If you take the history of technology as it was developed, it was all thought of from a commercial aspect. How do we get the product out to the marketplace? It wasn't near as much effort put to how do you get the rubber to the road. And so I think now we've seen in more recent times with companies like Allied, yourself, where you're spending a lot of effort on implementing procedures and stuff that makes sense. So we support that any way we can. So that's
Guys,
all good.
It.
Well, we're big advocates of the whole process. We really do. We enjoy it. We enjoy being in it. Well, it's really rewarding when we see customers and companies get a program implemented, started, and start to see results. It's just really great. And so there's a lot of successes.
It's good for everybody involved.
That's exactly right. And these guys that run these plants have I think traditionally kind of gotten a bit of the short end of the stick. They weren't the ones putting the product out the door from the eyes of the company. They were just keeping it running, and they weren't the ones selling the product to the customers. And so they were always the first one to kind of get hit over the head when something needed to be cut back, things like that. It was.
Oh, absolutely.
Yeah, so that's all been changing. Well, that's great. I've got some stuff coming here, Carey. I'll email you with the things that people sent here, so you'll get that. We appreciate it. I think we can get you back on another time for maybe we can do a little bit of a webinar on something on how to assign criticality or something like that. Would be great.
Sure.
We always enjoy having you.
Absolutely.
We've got another one of these scheduled for December 1st. We're going to have one on NFPA 70E and 70B, which actually has to do with electrical standards and arc flash safety and things like that. A huge topic that we find going around, people operating in safe environments and what we can detect. And we're going to, if anybody out there has ideas about other topics they would like to hear about, things they'd like to learn about, let us know. Or if they've got something they would like to share with our crowd, just let us know and we'll put it up there. We're committed to this continuing education, and however it is we can help people with things, we'll certainly do that.
Guys, I appreciate the opportunity.
Perfect.
Hope everybody got something out of it.
Yeah, we had quite a list of people on here. If there's any questions, please contact us. UE Systems, we're at 14 Hay Street. I've got our phone number and an email there. You can simply reach us at info@uesystems.com. I'm just Gary M at uesystems.com. Doug is Doug W at uesystems.com. You can reach any of us. Carey, how do they reach you?
Repasz C, so R-E-P-A-S-Z, letter C, at alliedreliability.com, or you can just go to our website, and there's quite a few different ways, you know, obviously in the contact us phase, and there's a lot of information on our site as well that basically you can go and request that you get for free. Yep. And that'll get you in touch with somebody. Yep. And if you can remember my name and want to talk to me one-on-one, just ask them for my contact information. But like I said, my email is repazc@alliedreliability.com. Perfect.
Well, and I think at that, on this note here, I think we've kind of reached our end of our line for today. Thank you again, Carey, and we'll be back in touch with you. Again, anybody has any questions, shoot them our way, and we'll take them up for there. Thank you.
Thanks, fellas. I appreciate it.
All right. Bye.